Good afternoon, everybody, and welcome to Compass. Today we have Sam Nebylitsa giving her 1 hour talk. Sam is a fifth-year PhD candidate supervised by Dave Nolan and Sharon Majumdar. Sam earned her BS and MS in atmospheric science from Stony Brook in 2019 and 2020. At Rosenstiel, Sam is president of GradOut and a member of the Flight School Committee. Formerly, Sam was also president of MSGSO. For all of her service, Sam was named the Outstanding Graduate Student Leader this past spring, and Sam will defend her PhD next semester, and we will miss her very much. So without further ado, Sam Nebylitsa.
Thank you. So today we're going to look a little bit on tropical cyclone intensification in relation to environmental and microphysical conditions. I'm still working on the microphysics part, so it's going to look a little bit more on the environmental and a little less on the microphysics. So we'll go over just a general background to make sure we're all on the same page for what I mean when I talk about the environment, as well as a little bit on tropical cyclone intensification theory. Then we'll go into the environment around TCs from reanalysis. What we learned from that reanalysis we'll put into our idealized modeling so we can learn a little bit more about kind of the structural processes of tropical cyclone intensification. And then we'll briefly look at what I'm currently doing on the microphysical uncertainties. So the background. What do I mean when I say the environment around tropical cyclones? So historically, it is the 200 to 800 kilometer annulus calculated from the storm center. So for example, you have a plot of any variable. This is relative humidity. We draw a circle 200 kilometers and 800 kilometers in radius away from the center, and we essentially do one average in that whole area. So it's a big area, it's a big average. You can see that already there's some discrepancies, a lot of variations in the moisture in that area, and so I'm kind of questioning, is that one value that we're getting enough? The 200 to 800 kilometer annulus has gone through several variations. It started out as a 0 to 100, there's a 0 to 500, but this is the one that's most commonly used, especially in the SHIPS output, so the Statistical Hurricane Intensity Prediction Scheme. When they talk about the environment, most of the time they still use the 200 to 800. And this way, you're not considering the TC itself within that 200, and the 800 is far enough away, once again, that you're not really considering the TC, and a lot of the outer rain bands won't be too much of an issue, but it's also not too far away, such as that 1,000 kilometers, that you're really like questioning if that wind or that moisture is really doing anything to the storm. When I talk about the wind, I mean the vertical wind shear, which is the vector difference between the 200 and the 850 hectopascal winds, and it includes both a magnitude and a direction. The 200 and 850 has long been used, mainly because when kind of all this was starting, we had satellite data that was very reliable at those two levels. And I'm not going to show it here today, but I did look at some additional levels. So what if we went one higher, one lower, and the results were pretty insignificantly different from the results from the 200 and 850. Moisture, we look at the average relative humidity of the 500 and 700 hectopascal layers, also known as the mid-tropospheric RH. So that middle level of our atmosphere is what is super important to tropical cyclone intensification. This has also gone through several variations in layers, as well as not using relative humidity. So in the current RI, so the rapid intensification index, they actually use total precipitable water, but they do still also calculate the 500 to 700, and that is commonly what we look at as forecasters. So that is the base level of what I'll be looking at. And so generally, we say that low wind shear and high relative humidity are more favorable conditions for TC intensification. So why is that? We'll look at some figures that I drew. So when you have a low shear and a high moisture environment, you see that my winds, so the red and the yellow, pretty similar in speed. So you're going to get a nice upright storm. You're going to get your inflow, you have your eye wall, your outflow at the top. These two lines at the bottom are indicating the speed, the intensity, so they're pretty big. as you'll see in comparison to my other figure. And we also have this circulation that goes in, up, and out, and this is what is fueling the energy. That is what is providing the energy for the storm to therefore intensify, and these blue lines like to be in this spot, and it is most likely in this spot when the storm is upright because of the low shear, and naturally when you have higher moisture, you just have more clouds and they're able to sustain themselves. Now the top image here is what it looks like if you look at it from the top down. So we have a nice circular eye, and then you have the clouds all the way around the storm. And so what we call this is a vertically aligned axisymmetric storm. So these clouds are symmetric all the way around our axis. Now, if we have a high shear and low moisture environment, now my yellow, so my 200 hectopascal winds are a lot stronger than my 850. So our storm tilts over, and now you can see that my blue arrows indicating the speed is weaker. Those blue lines that are signifying my transfer of energy and that efficiency, they are no longer where they want to be. And so this just kind of creates instances where dry air can now come in. Naturally, low moisture, you have less clouds, as you can see, as compared to when you have high moisture. And then also at the top, if you look from the top down, now we kind of see a concentration of the clouds on one side of the storm. And so we call this a tilted asymmetric storm. So I kind of want you to keep these terms at the bottom in mind, especially when we go through the modeling part, because we're going to look specifically at these parameters. This is just a generalization of why low shear and high moisture is good. So one final kind of part of the background is shear relative quadrants. So I just showed why the shear magnitude is important, but shear also comes with a direction. And so for example, if you have a westerly shear vector, so we're going from the west to the east, we can create these 4 quadrants around the storm. So kind of at the arrowhead is the down shear, and then at the start of the arrow is the up shear. And if you notice from my picture, a lot of the clouds were concentrated in the down shear and sort of up shear area when I have a tilted storm. And so in order for the storm to intensify to become that axisymmetric, again, that moisture needs to move all the way around the storm into this up shear right region. And I want you to keep that in mind, because we'll look at that moistening in the up shear right and how it could impact intensification. All right, so now that we have a little bit, what is our environment, how do tropical storms intensify as a result of it, why am I still looking at the environment? A lot of studies have done this, but now we're going to be using a little bit more of a complete full data set. We're also going to be looking at changes over time. So remember that one value that I said that we're calculating in that huge area? What does that one value mean? Also, our environment is not static in time, it is changing. And so we're going to be looking at how the changes of the shear and of the relative humidity in relation to the onset of intensification differ. And so a few studies have done that. They found shear could be decreasing prior to onset of intensification, and once again, that up shear moistening. So moisture in a particular region around the storm is super important. And we're also going to be looking at how these changes differ for different intensification rates. So we can kind of compare what happens when you have a much faster intensification versus a much slower, and also different annuli. So that 200 to 800 kilometers, pretty robust, it has been used, but we are going to look at a few additionals just to see if we can find one that maybe has a stronger relationship. So we're going to look at the Atlantic basin using ERA5 data for my wind and relative humidity. Every 6 hourly data point is a new event, so it could still be continuing from its previous intensification, but we're going to consider every 6 hours an independent event from 1980 to 2021, so that's a 42-year climatology. And we're going to be using the HERDAT2 data set just for our storm center, and we're only using storms that are designated as a tropical cyclone, so that means a tropical depression, tropical storm, or a hurricane. So I mentioned that we're going to compare to different intensification rates. Some of you might have heard of rapid intensification. That is an increase in the maximum sustained winds of at least 30 knots in 24 hours. And so a lot of these studies usually kind of take your RI cases and then they'll take sort of a subset of a slower intensifying or steady state to really do a comparison. But we really wanted to see what are the differences between all sorts of intensifying. So we have a slight intensifier at 5 to 10 knots in 24 hours, and then a moderate at 15 to 25. And these colors are going to be consistent throughout the presentation, so you don't always have to remember what blue is. We're also going to briefly look at what happens when we separate the Atlantic Basin into 4 different areas, because the Atlantic Basin is pretty big, and so what is kind of happening in the open Atlantic might not exactly match some of the characteristics that we're seeing in the Gulf of Mexico, for example. So first we'll start off with what is the actual shear and relative humidity in my environment. So these are probability density functions. So we have shear on the left, relative humidity on the right. At the top is the count, so that is the number of 6 hourly events that I have in my 42-year climatology. And so what we can see is that pretty comparant to other studies is that rapid intensification is more likely to occur when we have a lower shear value compared to our moderate and our slight intensification. With our relative humidity, we also see that the blue is more likely to occur at slightly higher relative humidities compared to our moderate and our slight. So that's good, you know, we're not doing anything crazy, nothing's being weird in our data. But the one thing that's interesting is the amount of overlap between the different intensification rates. So that's also what I'm saying when we can't really say that with one number, what is the storm gonna do? So even, you know, at say 10, 15 knots of shear, yes, RI is more likely, but we still have a fair amount of storms that do not undergo rapid intensification at what we would be considered slightly more favorable shear. The same thing with humidity. We can see that even though at our 40 or 50% humidity, yes, slight intensification is more likely. Our atmosphere is drier, is not going to have that much energy to intensify the storm, but we do still see some cases that undergo rapid intensification. This is the breakdown if we look at the RI onset locations for all 4 of the regions that I stated. And I would say it's fairly spread out, except for maybe kind of this open Atlantic. We are in a higher latitude. The SSTs could be a little cooler. But for the most part, we have RI in sort of everywhere in the Atlantic. And this plot looks very similar for my MI and my SI onset locations, except your number is going to be higher than 4. So just as an example, I'm going to show you what the shear looks like if we split it by basin. So once again, our probability density functions, and we can see that none of them look like what they look like for the entire Atlantic. The Gulf of Mexico is the most significantly different in terms of their average values and sort of their peaks of the shear values. The Yucatan and the Caribbean Sea are the least significant, where there's the most overlap in the distributions between the 3 intensification rates, and then our Atlantic is a little bit more similar to what we saw as a whole. But this just once again shows you that one number does not really mean anything, and the one number in the open Atlantic could, you know, cause a storm not to intensify, but it could intensify in the Yucatan or the Gulf of Mexico with that same value. So that's just sort of what the environment of shear and moisture looks like in the 200 to 800. And now we're going to investigate additional annuli around the storm center. So I mentioned they chose sort of that 200 to 800, so it doesn't include the TC itself. But what the TC is doing could be important to intensification. It doesn't just like sort of disappear. If we don't put it in our map, it's still there. And so we're going to look at this 0 to 250 kilometer radius in that purple, because I want to know what's happening in the wind and the moisture within the storm itself, and maybe how does that differ from the environment. I'm also going to be looking at a smaller environment, so a 100 to 600 kilometer, and that is shown in the blue circle. So we are considering a little bit more of the TC, a little bit less of that far environment, and I just want to see how that compares to our quote-unquote standard environment. And now this is when we're really going to investigate the wind and moisture changes relative to the onset of intensification. So we're back with our PDFs. We saw the ones on the right already. We have the 100 to 600 in the middle and the 0 to 250 all the way on the left. So the pattern within each annulus is actually the same. So regardless, if you look at the 0 to 250, the middle, or the 200 to 800, the RI cases always occur, are more likely to occur at lower shear and higher relative humidity. However, there is a general shift in that the inner core has the lowest shear and the highest relative humidity, which that makes sense. A lot of the moisture, that's where all your precipitation, that's all where your convection is sort of in that inner core region of the storm. Now, once again, a lot of overlap, but these are all statistically significantly different except for the RI cases in the 100 to 800 kilometer between the RI and the 200 to 800 kilometer. So that's sort of kind of a little concerning, saying that the shear doesn't change if you look at a slightly smaller annulus than what we're currently looking at. Now those changes over time, so that one value that I was mentioning, that average, what does that mean when you have such a huge spread? And that environment is not static over time. So what we're going to do is we're going to look at the changes in the shear and the RH relative to onset in a 4-day period. The X's are your inner core, the square is the middle, and the circle is the standard environment. And these were all normalized so that hour 0 is our onset time of each intensification rate, has a deviation of 0. So it's all normalized to the onset value, and that's just because the average value at each of these intensification rates and annuli is different. So I would have 9 lines going every which way, and we won't be able to see anything. But here you can actually see the changes. So the biggest difference here is between the intensification rates. So we see that in the RI cases here in blue, over the 2 days prior to the onset of RI, there is a decrease in the shear in all 3 of our annuli. However, for our slowest intensification rates in the green, we actually see an increase in all 3 annuli. Now some of you might be thinking, what is 1 knot of shear going to do? What is 2 knots of shear going to do? This is an average over hundreds, if not thousands, of cases. And unfortunately, while some of these changes are not significantly different, the majority of the storms do exhibit these patterns. So they are evident in the reanalysis data. We're going to look at now our relative humidity deviation, once again normalized to the onset value at hour 0. Now we see a different pattern between our inner core and our environment. So our larger intensifiers, our RI and our MI, are actually moistening prior to the onset of intensification, whereas they are decreasing in moisture in their environments. And for our SI cases, all 3 are decreasing. Now, to me, this makes sense because as the storm is intensifying, once again, I said a lot of that moisture is concentrated in the center. So relatively, when you have all that moisture rushing into the center so that the storm can intensify, your environment is naturally going to be drier relative to where it was before. We're going to go back to those shear relative quadrants because that upshear moistening that I pointed out is going to be super important. And so this is just showing the plots are located directly where they are on the figure, so we're all oriented the same way. And so we're going to look at this upshear right quadrant here. So what you will notice is that in the upshear right, the RI is the only quadrant in which there is moistening 2 days prior to onset. All the other 3 have a decrease in their moisture. The downshear right has a little bit of increase in the inner core, but for the most part, all 3 of the other quadrants are decreasing in their moisture, but we see upshear right moistening in this quadrant, which matches a lot of previous data. It also shows that the storm is attempting to sort of wrap around that convection from the downshear over to the upshear right. It sort of gets distributed, and that's why you see the relative increases and decreases. So to summarize the reanalysis part, we saw that the onset of RI is most likely to occur in low shear and high RH in all 3 annuli. the distribution of shear values do vary widely by region in the Atlantic. RI cases exhibit decreasing shear, while SI cases have increasing shear prior to onset, and moistening in the upshear right quadrant is evident prior to RI. So we're going to take what we learned, and now we're going to sort of input it into a model so we can understand a little bit more what's happening in the tropical cyclone. So I did all that math, I have all that wind, I have the moisture, I have the temperature, so I have a 42-year climatology of our atmospheric profiles of these variables, and so we can use it to create sort of RI and SI events in the model. And this is opposed to a lot of previous studies that use very simplified wind and moisture profiles, and so I'm going to actually be using what is observed in our atmosphere. And so the goal is to create a pair of TCs that have a distinct difference in their intensification rates by using these profiles from climatology. And a lot of previous modeling studies have only, once again, investigated RI versus non-RI in the model, and I will show you a little snippet of why that probably was. And basically the question here is, how does the environment affect intensification through intercore structure and thermodynamics? So what do those profiles look like? The colors changed, I'm sorry. Our RI is now red, our SI is now blue. We have the zonal and meridional component of the wind. A lot of those simplified wind profiles only use the zonal. And we have our average shear at onset from our climatology of 6 meters per second and 8 meters per second for the SI. On the right, you have the relative humidity, and in the black line is the Dunyan 2011 moist tropical sounding, which is the most commonly used sounding in modeling. When they need a moisture and a temperature profile, they will use this sounding. And as what you can see is that our climatological profiles, for the most part of our atmosphere, are drier than this profile that is commonly used, which says that you can get RI events with a drier atmosphere. And the only area where it's in the same range is that mid-troposphere. So that middle region of our troposphere is very robust in its moisture. So remember I said, why did they maybe not study non-RI events? This is why. This is all the simulations that I had to do to try and get a non-RI event. Just don't RI, just don't do that. You don't need to know what all this means, except that the beginning of the majority of these simulations start with SI, which means that I'm using the SI profiles. And I was still getting rapid intensification. So there was a lot of tweaking within the model realm to try and get a non-RI event. And for a long time, we were thinking, is this even possible? Does this even happen in the real world? Like, am I trying to do something that's like totally out of the question? And so I went back to that HERDAT data set, and I was like, okay, so we're obviously SI, I'm not gonna get 5 to 10 knots. The model is just not gonna do that. So I'm like, okay, let's go up to 20 knots. So even like 20 and 30, there's still enough of a difference there that I could start to figure out what is happening, what are some of the slight changes in the structure between the two storms. And so this is the count of the actual hurricanes from the HERDAT-2 data set. I extended it out to 2023. This is the lifetime maximum intensity that the storm achieved that underwent at least one RI event and had its maximum intensification rate throughout its lifetime was 20 knots per 24 hours or less. So while yes, in order to become a major hurricane, you have to undergo RI. That's just the way the world works. But you can get a hurricane with only increasing by 20 knots in 24 hours. So we're like, this does exist. We just have to figure out how to get it in the model. So there's a few ways that we got it. The first is with our model setup, in particular the radiation and the ocean. So a lot of idealized models don't include those. They do have additional, things that you have to consider. You're making it more complicated. A lot of people just want the simplest model setup that you can get. But we put in radiation and we also put in an ocean. So we have ocean-induced cooling. And these two definitely help bring down our maximum intensity of the storm, which as a result also brought down our maximum intensification rate. The other thing that we have to do is we have to force the environment. So we don't just take my profiles, initialize, and let the model run. We tried that, it didn't work. We have to force the environment to stay at those profiles so that we can really see how those specific values of wind and moisture are affecting our TC. What we did is we initialize actually with no wind shear. We have a weak vortex, 20 meters per second, no wind shear, and we also are using the RI mixing ratio and temperature. And we're gonna give it a little bump. We're gonna give it just, we're gonna let it run. And over the first 18 hours, we're gonna slowly increase the shear up to 15 meters per second. So 30 knots of shear is a lot of shear. And what this is doing is it is actually slightly weakening and slightly tilting and shearing the storm. And so the reason we had to do this, number one, is so that I can get a non-RI event. And number two is that in our atmosphere, we aren't just given a nice axisymmetric vortex. The storm is sheared, the storm is asymmetric, and that is how they intensify. And so we're able to, through this process, really understand how storms intensify from being a tilted, sheared, asymmetric storm. So after the first 18 hours, we bring the shear back down to either our RI or our SI profiles, depending on what we're doing. We also bring it down to the relevant temperature or moisture. So here, this is showing the difference from my RI and SI moisture, just because if I were to plot the blue line, it would practically be on top of the red, and you won't be able to tell the difference. So this is just signifying if I'm using the RI moisture, the RI wind, I'm also using the RI moisture post 18 hours. And if I'm using the SI wind, I'm also using the SI moisture post 18 hours. And I also want to note that this is only happening in my parent domain. So I have two nested domains that are following the vortex. And so the subsequent effect in those nested domains is going to be slightly delayed, and that actually helps our case in the sense that this 30 knots of shear is not going to totally destroy my storm. So just to prove that it worked, we have our intensity plot on the top. I have two ensembles of 5 members each that are just made from different random noise in my initialized wind field. We have the SI once again in the cooler colors, and we can see a big difference in their maximum intensification versus the cool color, the warm colors for the RI. So great, we have two very distinct intensification rates. The bottom, I'm showing the shear calculated in the 200 to 800 kilometer annulus, and we can see that we have that ramp up of shear, and then we immediately have a decreasing, and that it eventually does level out at my prescribed shear values. The effect on the storm, as I mentioned, is not going to be immediate. There is going to be a delayed reaction because that wind from the environment does have to penetrate through two nested domains to reach the inner core of the storm. And so we're able to slightly intensify the storm, and then really kind of once this peak shear takes over, you get a little bit of weakening, kind of this steady state, trying to reorganize, and then once the shear reaches it's the values that we want to investigate the storm at is when we start seeing the intensification. So great. After 6 months, I did it. So once again, we're going to look at everything relative to onset, because as you notice, all those lines, those big bumps in intensification, were happening at slightly different times depending on the ensemble member. So for RI, we're defining the intensification onset as the largest 6 hourly increase in V max. So I'm doing this because sometimes you might have the first few hours of your RI period be steady state, even though the 24-hour increase in Vmax satisfies the 30 knots, the first few hours might not, and so we really want the largest increase in Vmax to be the start of RI. And our SI kind of has two different conditions. So if my largest intensification rate was less than 20 knots in 24 hours, it's just the start of that time. And if it was greater than 20 knots in 24 hours, I use the start of the first 20 knots. So this is just showing the maximum intensification rates. The first number is the RI, and then the second in the italics is your SI. And we do pretty well. We have 2 that were below 20. We have 1 that's an outlier at 27. Obviously not as good as I would have liked, but there is at least a 20 knot difference in between my RI and my SI cases. So there's still differences that we could study, and we can see that most of the RI cases are in the mid to upper 40s, once again with one outlier. And then at the bottom, you just have the onset times, which are all different depending on the ensemble member. So the first thing that we're going to look at is that storm vertical tilt. So remember, a nice hurricane, in order to intensify, would like to be vertically aligned, so a lower tilt. So we calculate the vertical tilt by looking at the vorticity squared, but with the sign reserved. We take the centroid of that at the 0 and 6 kilometer levels, and we calculate the distance. And what we can see, we'll look at the averages. So the RI average is in that thicker red versus the SI average in the blue, is that at 24 hours prior to onset, it's only a day, which in forecasting terms is not a lot of time. The RI cases actually have, on average, a higher tilt than the SI cases. And it's actually not really until 6 hours prior to onset that they're lower. And this is also the time where they become statistically significantly different. So here, it could really go either way. So while yes, at onset, the RI cases do have a lower tilt on average, there is a slight difference through the intensification process. So sort of all the ensemble members converge towards the average for the RI case, but for the SI case, there's a lot more variability. They don't all converge towards that average. There's a lot of variability within the intensification period. So those slight changes in tilt over that 24 hours might induce a less efficient transfer of energy and therefore stunted some of our intensification. I also want to note that the RI cases had the largest drop in their tilt. So they had the largest decrease in their tilt value compared to the SI cases around 12 hours before onset. So we believe that it is the rapid vertical alignment of the storm that has allowed the TCs in the RI ensemble to undergo RI versus SI. We'll look next at the asymmetry, where I developed this calculation based on a few studies. So we have gamma, and it is essentially the ratio of the reflectivity perturbation over the azimuthally average reflectivity. So we're looking at it in the inner core, 20 to 80 kilometers, near the surface, 1 to 2 kilometers. And so basically, when you have a highly asymmetric storm, so while all of your precipitation is sort of in one area, those perturbations are going to be much larger compared to the azimuthal average, and therefore you'll have a higher gamma. Whereas if you have clouds all the way around, it's a nice axisymmetric storm, your perturbations relative to the azimuthal average will be smaller, and then therefore you'll have a smaller asymmetry proxy. So kind of a similar story as in the tilt. At 24 hours, they are actually exactly the same. And then over the course of the day, once again, we see that rapid decrease, so that rapid axisymmetrization of the storm. And then through the intensification process, we actually see quite a significant difference in my gamma value. So we're looking at the reflectivity to do this. We can associate these values with images. Each column is one of my ensemble members. I have the shear direction in that black arrow there, just so we can remember those shear relative quadrants, and we can see really how all this precipitation and that convection is in that down shear area, especially that down shear left region. So once again, if you were a forecaster and you were looking at this, it is minus 24 hours. We went back in time. You would not be able to pick out which storm is going to undergo RI or SI based on how it looks, unfortunately. If we go 12 hours into the future, we now have storms that look like this. So we have two of our SI members actually starting to form an I, and these two correspond to the lowest values of gamma here, whereas in the RI case, some of them are trying to, but for the most part, still very split in their distributions, in their visual appearance. And so, as I said, one might actually think that these two are going to undergo RI, but those actually undergo my lowest intensification rates. If we look at now our 0, our RI cases finally have the lowest asymmetry proxy, and now they all have a nice eye. We can see that there is convection all the way around. It is fairly evenly spaced out around the storm, which is why we have a lower value. Once again, they all also converge towards the average, whereas in my SI case, once again, we have some with an eye, some that don't. The convection is not all the way around. There's a lot more still in our left of shear region compared to the right of shear, and that is why we have a lot larger spread in our gamma values. So I mentioned these two SI cases that looked the best at 12 hours. They had the lowest actual intensification rate starting at hour 0, and that is because they only go from about 0.5 to 0.45. So not a big decrease, whereas all my RI cases have a large drop. So once again, it's that rapid axisymmetrization of the storm that allows it to undergo RI. So we looked at sort of what the effect of the wind shear is. Now we'll look at the moisture. And so we look at this at what we call ventilation, which is the sort of influx of low equivalent potential temperature air. So the lower the theta E, the drier the air is. And we're looking at perturbations relative to the azimuthal mean. So where W prime is negative, we have air going down. Where we have theta E negative, we have dry air, which we get positive, and positive is in our red. So our red is our downdraft ventilation. Red is bad for the storm. Once again, minus 24 hours, they look exactly the same. But we can see that once we get into sort of this 6-hour period before onset and onset, the downdraft ventilation in the RI cases, for all intents and purposes, is no longer there. But we still see quite a bit of downdraft ventilation in that left of shear region for the SI cases, and we believe that because of this persistent downdraft ventilation, this dry air that is still coming into the storm is what caused the SI cases to undergo a lower intensification rate. So downdraft ventilation is done at the 1 kilometer level, but I mentioned it's that mid-tropospheric moisture that is really important. So we can look at that in terms of radial ventilation at the 5 kilometer level. So U prime is our perturbation of the inflow, so we're now in cylindrical coordinates. So negative U is inflow into the storm. So negative U, negative theta E, once again, red, positive, bad. Minus 24 hours, same story as this whole modeling paper. We can't tell the difference between the two. At that negative 6 hours, once again, and on to onset, for the RI case, that radial ventilation, for all intents and purposes, not really there anymore. The SI case, however, has this persistent radial ventilation from minus 6 hours going all the way through the intensification process. Once again, this is our shear vector, and this area is consistent with the up shear right portion of our storm. And if we remember from our reanalysis, the up shear right for the RI cases was moistening. So we don't have moistening here, we have drying. And because that up shear right is unable to moisten, we believe that stunts the growth because it is within a 50 kilometer radius, so it is right in that inner core region. We're just seeing a lot of inflow of this dry air into the storm.
Sorry for interruption.
Yes.
Have you also looked at for minus 12 hours?
I did, and
How it look like?
it's like in between. Like, yes, there's like a little bit more at SI, but it's like the negative 6 was like the real big difference. Okay, so just to summarize, I've successfully created 2 ensembles with different maximum intensification rates from my reanalysis profiles. Unfortunately, though, the ensembles are not statistically significantly different until an asymmetry at 24 hours prior to onset, and it is the rapid alignment and axisymmetrization in the 12 hours prior to onset that preludes RI versus SI. And so if you're a forecaster, 24 hours is like no time. 12 hours is like negative time. When you have flights that are 12 hours apart, you're not gonna be able to get the data in time for forecasters. So That's unfortunate, but once again, it is an idealized model, so we have to keep that in mind. And lastly, we saw that the SI cases have more downdraft and radial ventilation right before onset, and so they have more dry air, which is inhibiting its intensification. So we're going to shift gears a little bit now to the microphysics part. And microphysics, small scales, they have to be parameterized in the models. So a few studies have tried to do this in what I call the bigger picture, where they really include either warm rain only processes, then they put ice in, they remove melting or evaporation, which are very important, energy and phase changes for the storm, for the hurricane, and they also compare different schemes. So in the WRF model, you have different microphysics schemes. They all have different equations. Naturally, you're going to get different answers, but that is what a lot of studies have done. And then there have been fewer studies on this part where they alter parameters within a scheme to sort of test uncertainties. And so you can do this by altering the particle size distribution, so you can create more smaller or more larger particles, vice versa. Or you can adjust the fall speed of the hydrometeors, which is what I'm going to be focusing on. And there's no consensus on the effect of the microphysical changes to TC intensification. So part of that is because we don't have observations. Yes, we can fly into hurricanes, but we can't fly where there's ice. And those ice processes are very important, especially because of the phase changes and the energy associated with that. So a little bit on the motivation on why we're looking at fall speeds and ice particles. So particle fall speed is commonly written as the velocity equals the coefficient A times your diameter to an exponent. This is from Locatelli and Hobbs, 1974, so it is 50 years old, but it is a seminal work of ice microphysics. And the equations that I have highlighted are the two equations that are in the microphysics scheme that I'm using. So we have one for grapple, one for snow. There's also ice, but that comes from a different paper. And what you can see is just a range of velocity values. You can see what it looks like if you plot the diameter versus the velocity. And I'm not going to say it was a random choice, but for all intents and purposes, it could have been a random choice because you have 3 different types of lump grapple, and they chose that one. And then you have different types of aggregates, and they chose that one. So there's a large range of equations that could be used, and you can get different fall speeds in the storm, but we're just using one. So what we want to do is we want to see what happens if we affect the fall speed of these hydrometeors within a scheme, and we can simply do that by changing this A value. So a larger A will make it fall faster, a lower A will make it fall slower. And so this way we can really see kind of the uncertainties between like actual bounds. As I said, like if they chose a different equation, we would naturally be getting a different result. And so all these are from snowstorm observations. They're not from a hurricane, so do these equations even matter? Do they line up? Nobody knows. So we're going to be adjusting the fall speed of the frozen hydrometeors, so just ice, snow, and grapple, to see how it affects the intensification rate and the onset time. There is rain in this model, but the fall speed of rain is fairly well accepted value, so we're not going to play with that. We are going to see eventually what impact this has on the environment and the TC structure. But we have a few kind of working hypotheses that faster falling hydrometeors will result in weaker storms. We have a few different kind of things we're looking at. So the first one is precipitation unloading. So if the fall speeds are faster, the precipitation is going to fall out of the clouds quicker. So you could get larger downdrafts, which are inhibited of intensification. And also, if all the precipitation falls out of the cloud, then you don't have a cloud, and then you don't have a storm. If they're falling faster, technically, there could be less evaporation time. And if you're not evaporating your particles, you could have more dry air, and we know that dry air is inhibited of intensification. On the flip side, depending how the math works in the model, if it's falling faster, it could be going through evaporation quicker, but then you could have more evaporative cooling. And we know tropical cyclones like warm, so if you have cooler air, it's not going to like it. But on the flip side, more evaporation. You could also be moisture. So there's a lot of kind of things we're looking at play. So I'll just show some initial results. We're still kind of testing to see what is the best route. So this is just the first two ensemble members from our RI and our SI case. The solid lines are what we looked at before, my quote-unquote control. The dashed line is a decrease of 75%, so we just decreased the A value of what was in the code by 25%. And then my dotted line, we increased the A value by 25%. And so what we can see is that when we have a slower velocity, we actually have an earlier onset and an either stronger or similar intensification rate for the most part. So a lot of these dashed lines are occurring earlier than the solid line, and also could be much stronger in their intensification. However, when we had a faster velocity, we noticed that there was a later onset and actually a much lower intensification rate. And you can see all these dotted lines are much lower in their intensity in general, but also their intensification rate is much lower compared to their solid and their dashed counterpart. And actually, none of the RI cases underwent RI. So we'll look at kind of just one variable, one theory, which is the drying of the atmosphere. So this is just the first RI ensemble. Remember, we have the original relative humidity plots. This is 6 hourly averages at these 3 times, and these 3 times were chosen because if we look at the actual intensity, they're all roughly at the same intensity still at that point. Then we have the 125% velocity, and because I can't really tell the differences here, we did the difference. So this is original minus the 125% at the bottom. And so where you have the red values, that means that the original is more moist than the 125%. And this is definitely kind of agrees with one of our hypotheses that when you have faster falling particles, you can get less evaporation, and therefore our atmosphere is drier. And we're seeing that because our middle of the troposphere is more red, which is saying that our original case has more moisture than our faster falling case. So there is evidence that if we adjust the fall speed, it could have impacts on onset time and intensification rates. And initial results indicate that faster falling particles do result in a drier mid-troposphere, which inhibits intensification. So what I'm currently kind of working on and playing with in the model is adjusting individual hydrometeors. So I changed all of the frozen, but the previous studies have done this, have only changed one at a time. And so this way we can really isolate the effects of snow versus graupel versus ice. We're also thinking about introducing the altered fall speed 2 days into the simulation. So now it's there at the beginning through sort of that weakening and that shearing phase, and we don't really want it to impact that. So we want to see what happens only when we want the storm to intensify. And then, we'll continue kind of looking at the environment. Are we seeing cooling? Are we seeing drying? Or are we seeing moistening? And then any structural differences that might come about. So that could also be like the size of the storm and not just kind of the tilt and asymmetries. And I will take any questions.
Any questions in the room? Michael.
I have multiple questions, but I can ask some later. That was really cool. Can you go to the slide with the radial ventilation? So you say that there's not pronounced differences, but especially early on, minus 24 hours. But it looks like there's an azimuthal shift in the differences between R and SI a little bit.
A little bit, yes.
And for example, Josh Allen's work on this, and some like Mike Gonzalez's study too, showed that the pattern of radial ventilation is closely tied to the tilt direction.
Yes.
So are there differences in the direction of the tilts, essentially more precession that you can then actually snowballs to the
Yeah, so I did look at like the tilt direction and like the angle of the tilt, and I couldn't really pick out any differences. It was very like messy and back and forth between the two ensembles. So Yeah, because I did see that in Josh's paper of the tilt direction, and I couldn't really find anything significant on the direction of the tilt. I found it was slightly more aligned with the shear direction, this split, but not really with the tilt.
The SI cases had a tilt direction that was more aligned with the shear, you're saying?
No, just in general, like the radial ventilation I thought was more aligned with, like the split was more aligned with the shear direction versus the tilt.
Oh, really?
Yes.
Okay. And then, okay, my second question is related then to the downdraft ventilation. Were there differences in like the vertical mass flux profile for the times leading up to the tilt reduction?
I did not look at those.
Okay. So I'm just curious if there's differences in convective structure, because some studies have emphasized that's what's driving kind of the reduction in tilt. So I'm wondering kind of what time scales you can maybe see that evolve.
Okay.
Thanks.
Okay.
Any questions on line, Roland?
No.
I have a question.
Yes.
In one of the early slides, you had two different schematics showing the axisymmetric versus the asymmetric.
I like my drawing.
Structures. Yeah. And the drawing that you had for the asymmetric had an eastward tilt. I was wondering if your the selection of your storms from PERDAT 2, perhaps it was like the modeled storms where you had tilt. Were you isolating like a tilt in one direction or the other, or was that tilt specifically the westward tilt with high or eastward?
So the tilt directions in the model were all fairly similar, and then in like the reanalysis, they are all on average. You have on average a westerly shear, which is this way. So on average, they're all going to look like the picture that I showed, but there are slight differences. But yes, does that answer the question?
Yeah, it was
Okay.
just general curiosity.
Yeah, so in the model, regardless of the intensification rate, they all had a very similar like tilt angle and where that tilt was in relation like to the center of the storm.
Dave.
Hey, Samantha. So, well, I think the elephant in the room is the fact that your tilts, right? The RI tilts start out larger.
Yes.
Right? Have you thought about? You share with us any thoughts you've had about why that is, or maybe you know more simulations you could do to figure out what's going on there?
Yes. So we'll go back to that plot. I did look at the reflectivity of the kind of near surface and then the 6 kilometer. The tilt is calculated from the vorticity, but I think with the reflectivity, it's a little bit more visually apparent. And so what I did notice is that in some of the RI cases, you have a slightly more widespread region of higher convection. And so I'm thinking that is what is slightly pushing the centroid of the vorticity further away, whereas in the SI cases, it seemed to be a little bit more closer.
You mean like a larger cloud shield?
Yeah, there's a larger cloud shield in the RI cases, and so I think that partly might be why. I do think part of it is a resolution issue of, it is an iterative method of calculating the centroid, but still I think even 1 to 2 grid points could be like 4 to 6 kilometers, which could contribute to the difference. But that was what I looked at, was the cloud at the higher levels seem to be a little bit further away. Yeah.
By region, in the Atlantic you discovered in the RI cases signal for the pathway for reduction of vortex tilt, whether it was reformation or recession?
I did not look at like tilt or anything by region of the Atlantic. Those were mostly just like the variables, like shear, relative humidity. I looked at the SST by region, but nothing in relation to the structure. That is something that can be done, but I did not look at that. Okay.
I think that's it. All right, we have our first three 15-minute student seminars this Friday for Compass. So we hope to see everyone and more friends there on Friday. And thank you, Sam.